All right, chapter 4.3, talking about Extrema. All right, so this is a topic that we have covered, all right, but we're really going to kind of just make sure that we have the right words and that we kind of just get a better understanding of the idea. All right, every continuous function on a closed interval, all right, so pick two values of x, has some form of an extreme or an absolute minimum and has some form of an absolute maximum. All right, and we call these values extrema. Okay, it might be the endpoint of that closed interval. It might be somewhere in the middle. Okay, but this idea is called the extreme value theorem. Okay, if you have two closed endpoints, okay, so for instance, a closed endpoint and a closed endpoint, and it's a continuous function in the middle, there is one point that is the absolute lowest in that function, and there is some point that is the absolute highest in that function. Okay, so the domain of this function is from what? 1 to 4, right? And we have two extrema. We have this spot right here is our absolute max. All right, and these are coordinates. All right, so 4, 4. All right, and our absolute min is right here, and we can say that's what? 2, 0. All right, so something that we've definitely done before. We kind of understand this idea. All right, this next one though does produce a little bit of a challenge. Okay, so the problem is this function itself is not continuous. These two pieces don't connect. Okay, and this first piece, the piece on the left, it has this open circle. All right, that is called an open interval. Now, we cannot say where the absolute lowest is in this open interval. All right, you could say it's what? It's getting really close to -2 here. But if you tell me a number that's really close to -2, I can tell you a number that's even closer. Okay, then you can tell me a number that's even closer, then I can tell you a number that's even closer. Okay, so the problem is open intervals do not necessarily have an absolute, in this case, minimum. All right, they have to be close bounded. Okay, so we can only look at this one, this piece, if we're going to talk about an absolute minimum and maximum. This piece, we could say that's an absolute max, because that is close bounded. All right, but this piece, we cannot say where the minimum is. Now, this will have both an absolute minimum and a maximum. Great. All right, and then just while I am talking here, if there is, let's say, a closed bound and it's just a straight line, all right, it's just a flat line, closed bounded on both sides. The question is, where is the absolute minimum? Where is the absolute maximum? Well, the answer is everywhere. Everywhere would count as both the absolute minimum and the absolute maximum. Okay, every value in the bound, all right, would count as both. Okay, it doesn't say that there is only one. It just means that, yeah, there could be a bunch. Okay, all right. So I hope this makes sense in general. Absolute minimums, absolute maximums. They could be edge points. Okay, they have to be close bounded bracket intervals. All right, and it has to be continuous for this to work. Now, if you want to talk about what's called a local or relative extreme value, that's when you look at the entire function and not just a smaller subset. Okay, so like looking at this one, remember how we just talked about this piece, all right? So like this compared to the whole thing would be a relative maximum, where that would be the absolute maximum. Okay, hope that made sense. This one is higher than this one. This would still count as a maximum, just not the absolute. It'd be considered a local or relative maximum. All right, so how does this relate to calculus? Because this just sounds like, a fancy way to talk about things I've already learned. I learned about this in Math 171. All right, we found these things. We labeled them. We did this, okay? So the way that we do this here in Math 171 is by finding these things called critical values. All right, critical values are spots in your function such that the derivative is equal to 0 or the derivative is undefined. Okay, when one of these two things happens, I know something weird is happening at or to our function. All right, so for this function here, this spot that I would consider to be what, a local maximum, the derivative here is 0. Okay, well, that's the general idea. When the derivative is 0, something special is happening. Okay, it might be a local maximum. Here, the derivative is undefined. Okay, it's continuous, that's great. But right here, the derivative is undefined. A sharp point, the derivative is undefined. So I know something strange is happening right there. All right, here, the derivative is undefined, a sharp point. So again, it's undefined. I know something weird is happening to my graph. Here, when you have kind of one of these cubic function looking things where it changes direction like that, something weird is happening. It levels out for a second, but it's not an extreme maximum. It's not, it didn't change from going positive to negative right there. It didn't change directions. It didn't go from increasing to decreasing. It just kind of leveled out for a second. So it's something I would want to take a look at, but nothing actually special happened. Here, our derivative is undefined. It's vertical. Okay, and again, something weird happened, but it didn't really change directions. It was increasing and it's still increasing. So it is not, in fact, an extreme value. It's just something that, we would want to take a closer look at. But in general, the one thing all of these have in common is that your derivative is 0 or your derivative is undefined. We care about these spots. Okay, so if you are ever asked to consider on a continuous function to find any extreme values, okay? To find any extreme values, you do kind of the following 3 steps. All right, step 1, just find the value of the function at the endpoints, okay, of the interval. Just find out what the value is here. Okay, so for this one, we need to plug in -1 and we need to plug in 5. All right, so 1/3 times -1 cubed minus 5/2 times -1 squared plus 4 times -1. All right, so I know that this polynomial function is continuous. No question about that. And I know that at -1, just making sure I type this in right, we have a y value of -6.83. All right, if we then plug in +5, we're at -0.8. All right, so we'll start way down here at -0.6, and we end up here at 0.8. All right, so I know it starts here and it ends there. Okay, cool. All right, find any critical points that lie in that interval. Okay, so to find critical points, you take your derivative. So 3 times 1/3 would just be 1. 2 times -5/2 would be -5x plus 4. We set that derivative equal to 0. Well, that is a quadratic. Okay. So does this quadratic factor? Front number is 1. That's good. So I just looked at the back number. What multiplies together to get +4 adds to get -5. That's -4 and 1. -4, -1. So our two solutions here would be x equals 4 and x equals 1. All right, these are both inside of this interval. That's good for us. All right, and so we want to then evaluate the actual function at these two spots. All right, so we evaluate the actual function at these two spots. All right, so here we have negative 2.6. Here we have a positive 1.8. All right, so compare these things. Compare all of these. All right, and we kind of know what's going to be what. The lowest of these four answers is our absolute minimum. Okay, great. So we have the absolute min here. And the highest value was this one at x equals 1. Great, and we've got this. Okay. All right, the question though is, what about like these other two spots? Okay, would we count them as relative minimums, relative maximums? What do we know? All right, our endpoints are never considered, well, I guess they could be. We would consider them to be a relative minimum or a relative maximum given that situation. All right, but the middle point we do kind of want to figure out. So one thing that we can do is create what's called a sign chart. Okay, so a sign chart says of these two values, don't really worry about your endpoints. You kind of know what's going on there. Write down your two values, 1 and 4. We know our slope at these two spots is 0. But what about before this, and what about in between these, and what about after this? Okay. So if we plug in a number smaller than 1, like 0, and we plug that into our derivative, 0 squared minus 5 times 0 plus 4, we would get positive 4. So our slope here is positive. You see how it goes from here to here, we have to increase. All right, so it's always increasing from here to here. Between 1 and 4, so a number like 2, if I plug 2 into here, 4 minus 10 plus 4, that would be negative 2, so a negative slope. Notice how we are decreasing from here to here. And then if I plug in a number bigger than 4, but still in my bounds, like 5, all right, into our slope, into our derivative, 25 minus 25 is 0, plus 4 is 4. So yeah, we are going to be increasing. All right, so that then tells me that that spot would be a relative or local minimum. Right? We change directions from a negative slope to a positive slope, so it would count as a local minimum. All right, to do this with a slightly more complicated function, all right, step 1, we plug in our bounds. All right, negative 2 squared is positive 4, minus 1 is 3, 3 cubed is 27. 2 squared is 4, minus 1 is 3, 3 cubed is 27. All right, so these both go to a height of 27. We do G prime. That's a chain rule. 3 times this thing minus 1 squared times the derivative of the inside, 2x. All right, we then want to set that equal to 0. 3 times 2 would be 6x times x squared minus 1 squared. All right, well, to solve this one, really I need to look at this inside part, and it does, in fact, factor. That is a difference of squares. We see how we're squaring this, so then I have to square both of those two factors. All right, so our critical values would be x equals 0, x equals 1, and x equals -1. All right, our heights at those values. If I plug in 0 to this thing, 0 minus 1 is -1 cubed is -1. 1 minus 1 is 0, cubed is 0. -1 squared is 1, minus 1 is 0, so again, 0. All right, so I have these 4 spots. Now, these two would combine or tie for absolute masses. The absolute minimum would be here. All right, and there was no spot with an undefined derivative or anything like that, so I know those. All right, these other two, I would like to maybe do a sign chart to figure out what's happening. All right, so I put them on here, -1, 0, 1, and I'm looking at my derivative. All right, so what I'm going to do is I'm going to plug into my derivative, into this thing, a number smaller than -1. Okay, so 6 times -1.5 maybe, and then -1.5 squared minus 1 squared. All right, that derivative is a negative, so my function is decreasing. It hits -1, and it has a slope of 0. In between -1 and +1, so like -0.5. Our function also has a negative slope. From 0 to 1, so if I plug in 0.5, positive, my slope changes to positive. If I plug in a number larger than 1, it is also positive. All right, so the general idea, our function had these values, -227, +227, 0, -1, -1, 0, 1, 0. All right, so I know that these were my maxes. Okay, that's easy. But from here to here, the graph was decreasing. The slope was negative. It has a 0 slope, so it kind of like leveled out for a second. But then it continued to decrease until it got to this spot. From here to here, the function then increased. It had a 0 slope, so it did level out for a second, but then it continued to increase. So these two spots, the slope didn't change signs from around -1 or around +1. All right, so these are what we call saddle points. They're like this thing up here, where yeah, the slope had a slope of 0, but nothing special happened. Okay, so these are not critical points. I mean, they are critical points. They're just not extrema. They're not maximums or minimums. They just exist. Okay, so our extrema are just these 3. All right, these 2 are critical, but not extreme. All right, number 3. Whew, we've got a lot to go. All right, number 3. We plug in our endpoints. Right, -12 over 10. Plug into 8 over 5. Okay, h prime. This derivative, well, that is a quotient. So the derivative of the first times the second left alone minus the derivative of the second times the first left alone, all over the bottom squared. We set that equal to 0. Now I would probably distribute this. These two can combine. A positive 4x squared and a minus 8x squared would make a negative 4x squared. All right, so when you set an equation like this equal to 0, now technically we can put this over 1, we can cross multiply. The bottom of a fraction is never going to be the thing that makes this equal to 0. Okay, so we don't have to worry about this. Okay, now the bottom of the fraction might produce an undefined value, okay, where the bottom would be 0, would be an undefined value. Can the bottom of this function ever be 0? Well, can you do a number squared and add it with 1 to get 0? The answer to that is no. It is never undefined. Okay, so not worried about any undefined slopes. So I just have the top of my function when it's equal to 0. Well, I can factor out a 4. I can factor that. Difference of squares. So our two potential critical values are x equals 1 and x equals -1. I have the plus 1 first, so I should say x equals -1 and then x equals +1. All right, if we plug these into the original function, 4 times -1 is -4 over 2. So we got -2. If x is +1, I got 4 over 2, so y equals 2. All right, it looks like this 2 is the highest value, so that's our absolute max. -2 is lower than -12/10, so this would be our absolute min. All right, I don't need to worry about those two spots on if they're saddle points or if they're extreme in this case. They're not. These are bigger and or smaller y values than those two, so I don't even need to worry about them. That's what I got. All right. I'm going to skip these last two. I hope that's okay. We kind of keep doing that same idea. I'm running at about 22 minutes already on this video, so I'm going to go ahead and skip to these last two to talk about critical values of any quadratic or any cubic. All right, so for any quadratic, we can find the extreme values, the critical points. Take your derivative. All right, 2 times a reduced by 1 plus b, derivative of just a constant, a c, would cancel out. Set this equal to 0. Subtract the b. Divide by 2a. And wouldn't you know it, that looks really, really, really familiar. That was the formula for the axis of symmetry in a quadratic. All right, we used to use this formula all the time to find the minimum or maximum, the vertex point of a quadratic. It's a formula we used all the time, and calculus is how we actually derive that formula. All right, you take the derivative, you set it equal to 0, and we've got ourselves our derivative there. I'm sorry, our vertex, our axis of symmetry. All right, for a cubic function, if we do our g prime of x here, all right, 3 times a, 2 times b, plus c, derivative of just a constant would be 0. All right, so to do this one, to set this equal to 0, well, that's a quadratic. We would have to do the quadratic formula. All right, so any cubic, to find these critical values, we would just use the quadratic formula. Now, in this case, I just wanted to write the quadratic formula. Not nearly as useful, not nearly as fun of a formula. That's what 12ac over 6a. Definitely never something you would memorize, and you don't see that pattern when you're finding these things, but you would in fact just use the quadratic formula if you're ever finding the critical values of a cubic function. Okay, they just come down to the quadratic formula. But this one, that's a formula that you should recognize. All right, and we should be able to handle that. All right, good luck on these. Again, the goal of finding critical values. All right, check your endpoints for their heights. All right, find the critical values where that derivative equals 0. Find those heights. Compare. All right, maybe use a sign chart. All right, of your derivative to figure out, did your function change direction? Are these critical values extreme values? Or did our function not change direction? Did the slope not change? All right, and then therefore these are not critical values. I'm sorry, they're not extreme values. They are still critical. Okay, and that's the general idea.